Okay, let's go look at this project now. Huh. Hey. Oh wow. There's just a lot of that's kind of annoying the way that it does that, but whatever. Maybe I'll move them all into like slash scripts or something. I don't know. Whatever. Alright, I'm not logged into here, but I will mention this on Twitter. Those little kids outside are just, I don't know, they're just having a great time, honestly. Just walked over the window and looked at them. They got one of those little tiny playhouses, and they're all just running through the door over and over. And oh well. All right, let's see. Oh yeah, I was gonna mention. I guess I should retweet it, and I should also. I feel self-conscious about loving my own posts, so I won't do that. Oh, I guess I can love somebody else's post. That's all right. All right, I'll do that too. And what else? I should leave a comment saying. Okay. Let's... Does Twitch still have a word limit on it? Beyond its integration. I thought I just sent it. Maybe I don't know how to reply. Hmm, that's interesting. When I look at my thing on Twitter, not logged in as myself, my comment shows up at the bottom, which I think makes sense. But if I look at Twitter as myself, on my other computer, I'm doing this. My comment shows up at the top. Is that the correct? It is. No, I don't know. It is also very cool for creating small scripts like this. All right, yeah. So I think that's it for that. And oh, I should stop streaming. Alrighty. Um, Number 4-5, validate BST. Okay, it's a very short description at least. So oh, okay. Chapter 4, problem 5, validate BST. That's the OJ. Yep. And so yeah, obviously I didn't even come close to finishing all 5 problems yesterday. I finished 2, I think. One in chapter 4 and one in chapter 8. And when that happens, I'm just going to actually the day before yesterday. And when that happens, I'm just gonna move on. I mean, it's Friday, the 5th day, so I should be doing the 5 problems. Um, Obviously the different chapters have different numbers of problems in them. So at some point, I may be cycling. And then I'll just start filling in the problems that I was not able to do. So reasonably speaking, there's going to be more problems in chapter 10, chapter 16, and chapter 17 that I haven't done than there are in chapter 4, right? Which hopefully at least most days I'll be able to finish one chapter a day. I didn't do any work yesterday. Um, I yeah, I had other things I need to work upon, and I did add a README though to CTCI. So I don't know. That's something. Okay. So this is 4-5. Validate BST. All right. Validate BST. That is implement a function to check if a binary tree is a binary search tree. Okay. So obviously this takes a tree. And I think it just takes 2 arguments. It sounds like I'm not sure exactly what they are right now, but I guess the expected is going to be true or false, and the thing is going to be a tree. Um, and oops, wrong directory. Yeah. Okay, cool. So, alrighty. So first thing I got to do is figure out that I. So what do I think? What do I think a binary tree? Well, I know what a binary tree is. Do I know what a binary search tree is? I think that's a tree that has the property that every child or every node in the tree has a child whose left node, for every node in the tree that has children, the left node is less than or equal to your node, and the right node is greater than your node. That's what I think that means. But let's make sure. Okay, a binary search tree is a binary tree in which every node fits a specific ordering property. All left descendants are less than or equal to n, are less than all right descendants. Okay, so I think we got it right. And so, it actually isn't that hard. So we can do kind of what we did yesterday on the chapter 4, where we did the next thing over and over again, you know? And maybe that's the right choice, honestly. Because all we need to do is basically say, hey, let's just go through every single node and make sure that for every single node, does a binary search tree require balance? Technically speaking. This must be true for each node. And the definition of binary search tree can vary slightly with respect to equality. Under some definitions, the tree cannot have duplicate values, and other duplicate values will be on the right or can be on either side. All are valid definitions, but you should clarify this with your interviewer. Note that this inequality must be true for all nodes' descendants, not just immediate children. The following tree on the left, okay, that's fine. When given a tree question, many candidates assume the interview means binary search tree. Be sure to ask. A binary search tree imposes the condition that for each node, its left descendants are less than or equal to its current node, which is less than the right descendants. Okay, yeah. So I don't think it technically means that the tree is balanced at all. Okay, so we just need to basically walk through every single node, ask is this node, and I keep doing this, but let's stop doing the node thing. Let's start calling them nodes. Okay, yeah. And so let's so we did 4.2 problem 2 minimal tree with the with the closure.zip, right? Didn't we? Maybe not. Chapter 4 problem 3 list of depths with the with the zipper, right? But let's try to use. But we didn't use the walker at all, actually. Let's try to use the walker this time because I'm just a different way to do it, right? So we could do the zipper. We could just create a zip. We could create a zipper, and then we could just next on every single node, and just we could do that actually. In fact, if we just copy this code right here, I'm pretty sure that's all we need to walk through all the nodes, and then we just basically ask the question for every node: is if there is a left node, if there's a first node, is the first node value less than my value, and is the first node's value, or is the second node's value, if there is a node, greater than my value, less than or equal to the left one, greater than for the right one, and that's it. But rather than create a zipper and do that, let's give it a shot just to use this walk thing, just because it's been a long time. Well, actually it's not, it's been, but let's just try walk, just to give it a shot. Now walk isn't quite as generic, but I think ultimately we're going to end up, the only thing that will end up being a thing we care about is the maps, right? So I'll show what I mean in a second. So I think like walk has a few different options in terms of what we can use it for. So I probably open this up. Let's see. Yep, here we go. So the first thing you want to do is just, it doesn't really matter which one you do, but I think for our case at least, we might, well, let's just see what this actually gives us. Interesting. So that actually just gives us, I thought it would give us, oh, it does give us, no, I thought it would give us a sequence of things it's walking. Oh, yeah, it is. Well, it doesn't give you a sequence, but it gives you this right here. You walk to the empty node. Okay. But what if the empty node contained, and every node should have a value, right? Let's just see what that actually prints. So as you can see, the way it walked it is it walked uh, the keyword and then the value at that keyword, effectively the thing in that keyword, right? Or sorry, I said key. Well, I did, but the key and the value within the thing, and then it walked up to the container for the thing and the value of the thing. Now you could have, I believe, replaced any of these things. You could have changed the return value if you actually were doing the walk. If you write the walk function yourself, you can change the return value. Like you could make it so that all keywords become strings, right? By just doing a walk and saying, anytime I see a keyword, I'm just going to replace it with the string equivalent of that keyword, right? Or you could change all integers to floats, or you could change all maps to something that you could change maps to, which I can't think of anything right now. Sorted sets, sorted maps, right? You could change, you could do that, right? Um, but we're basically going to do maybe closure.zip is kind of more appropriate for this. But what we're going to do is basically just filter so that the only thing we care about is the maps, right? Because that represents whole nodes, right? Everything else is not a node. It's you know I forget what this is called actually, like a key set or something like that, or and this is a this is obviously an integer and this is a keyword, so but anyway, so let's just look at what it actually looks like when we walk through different things. Um, Whoops. Oh, we got a few. We got value 2. Oh, that was weird. We also have value 3. And so that's a bit confusing because we got everybody printing at the same. The number of args is mesh. I beg to differ. So that should be. Is this balanced? Or sorry, is this sorted? No, it's not actually. If we want it to be sorted, this would need to be 2 and this would need to be 1 or 2. We're not even really worried about that right now. Okay, so this guy walked children, value. I kind of don't quite get how it's. So it walks. I mean, I guess it is. It says it in the name. It's a post walk. Let's just see if we can glean a little bit of information. Performs a depth first. Yes. Okay. Post order traversal of form. So it goes as deep as it can every single time. So as deep as it could go was into, basically it went into this first, right? And then went even deeper into that and went to this first. And this is the first thing it actually post-walked, was the children. I wish it would actually do some indentation to sort of indicate its walking path. Anyway, none of it really matters because the only thing we're going to do is basically look tell me when you show me, filter on all these, but just filter on the ones where you have an actual map, which there should be 3, but I only see 2, so I'm a little bit concerned about that. I see 1 map. I see 2 maps. Oh, there's the 3rd one. Never mind. Okay, so then yeah, if we have that, we just need to basically just ask some questions like, so we're gonna. So I think like one thing we could actually do is just. Oh, this is actually for changing it. This is not common closure code. We're going to start with the empty vector, right? This is a somewhat odd way of doing this. Because I think the purpose of walk This file designs a generic tree walker. It takes any data structure, blah, 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 calls a function on every element, and uses the return value of the function in place of the original. So walk is made to change the original. Let's just look at what pre-walk gives us. I think this one's a little too complicated to really follow through, so let's actually look at this. Let's not do anything yet. Where did I put save? Oops. Okay, so post walk is children value 2. I guess it is post walk. Let's see what pre walk looks like. Pre-walk demo, recursive pre-walk, like post-walk, but as pre-order traversal. So this guy hits the root node first, then it hits this guy, then it goes to here, then it goes to here, then it goes expands this into here, expands this into, it seeks on this and gets this, it takes this, says cool. Now it's recursed all the way back up to having rebuilt this thing, basically. I find this one easier to read, honestly. Not that it really, I don't think which one we're doing really matters at all here, but actually this one is maybe slightly better in that we can short circuit, right? The moment we can short circuit at the node that we actually failed at. I mean, I guess it doesn't really make a difference, but anyway. So we're going to pre-walk the node, but pre-walk actually does require a function, which would generally change something, but we're not actually going to change anything. So what we're going to do is just I wish there was a way to just make a sequence out of this. This isn't a good use of pre-walk, but I'm going to do it anyway. What we're going to do is, if it's a map, boom, right? Then return boom. When it's a map, then swap onto a conj this, right? We do that, so that's the when. And then the second thing we're going to do is just return the value, right? So we're not changing anything, right? Because this just does something to an atom on the inside, but all this function actually does, ignoring the part I've highlighted, is just return its value back. So it's actually the identity function from a value point of view, from a value returning point of view. So I'm going to do that, and well, that does kind of suck, right? Because well, we can't do threading on that because it doesn't really have a thing. But what we can then do is just say, okay, at a, once we've done this, we can say at a, so that dereferences the values at a, and then we can say filter out. Actually, let's just do that. Let's see what we got. So pretty much the same thing, right? Because, right, is that true? Let's see. The expected was false, and the value is this vector that contained one map, two maps. Oh yeah, I forgot we already filtered on the map. Okay, so that just contains the two nodes, basically. And we're going to ask the question, let's think about how to best structure this. So the BST node is going to contain children, right? And you do need to put that in a vector. And the children are going to contain a left and a right, potentially. And it's actually not true that it will contain children or that it will contain a left or right, but we can OR and say if there is a left, then it needs to be the case, oops, you also contain a value. It needs to be the case that left is less than or equal to your value, right? Similarly, if there is a right, then it needs to be the case that that value is less than right, right? So I think we can just say this, all right, if we remove all the ones that are BST nodes, and we're left with, and we are empty, all right, then we know that every node was a BST node. We've walked through every node. We got every node here. We know that every node is a BST node, and so now I can do empty. I'm kind of thinking that maybe we just don't want to do the filter here. Just swap everything into the thing. We can do the filter here. I just feel like that makes it a little bit clearer. I think I'm going to stick with that, yeah. So filter on maps, right? We only want to keep the maps. And this actually doesn't need to exist at all. And now this guy can just be the identity function. Whoops, nope, what am I saying? This guy does need to put stuff into the, so swap into a, conj, whatever you have, right? So then we grab the A, or dereference it, the value within it. We filter out everything we filter only on the maps. We then remove all of them that are BST nodes. And then we say, is this empty? If it is empty, then that means everybody was a BST node, and so we're done. If it's not empty, then that means we got problems, basically. So, okay. Let's see what we got. Ooh, we got some crazy. All right. Oh man, I hate these errors. It's just, I'm sure it's gonna scale off the screen, and I can't even see it anyway. Yeah, I gotta figure out how to increase that too. That's just ridiculous. 1,800 characters. We're in the 21st century, my friend. I mean, okay, what have I done that might be causing this? Now let's just comment out everything. That's weird. That should cause something to happen. Golly, that's annoying. Okay. Validate BST. Okay, so we do know that walk, pre-walk is finite, right? I don't feel that this can be anything but finite, but let's just start randomly commenting out stuff. All right, so it's evidently not a problem with that. So it actually is a problem in walk. What if I just do this? Weird. So it's actually a problem with walk, pre-walk. Oh, I see what I did. I didn't return the value. Well, I don't know. This doesn't really look any better than the function I built up there, and I don't like. Okay, so let's just do the function again. Okay. Could not resolve percent. Yep. Lame. But at least it's not a huge one. Oops. Whoa. Oh, whoops. Thank you. Other. Closure lang persistent array map cannot be cast to Java lang number. That shouldn't be happening. What's going on there? Something on the less than or equal to, which is right here. You're saying left. Oh, you're right. It's not a. It's the left value is what we want, not the left. It's the right value that we want, not the right. I'd say just. Do we want to be clever about this? Sure. Okay. Okay. Alrighty. So let's get some that actually should be equal. Or that should be. How would this guy become a BST? Let's do this guy first, actually. How would this guy become a BST? Well, this guy needs to be 2 and this guy needs to be 1, right? Okay, so that failed. Okay, how would this guy become a BST? This guy needs to be 2, this guy needs to be 1, this guy can be 3. That should be true. Alright, so you got 2 failures. Why are they failing? I'm gonna guess the BST nodes. Oh. First of all, should this be an OR? So if we... Oh, this is almost like... I'm just gonna say if left, do this, otherwise return true. And if right, do this, otherwise return true. And this is not an OR, but is an AND. So now we have a guy who is true. Well, I guess that is actually true. I was wrong, wasn't I? This guy should be a BST. We should also technically be passing on the case where you are the same as your child, as your left child. Let's check for both of those. Right, both the empty case and the I have 2 arguments cases. Okay. Alright, okay. I think that's about it. Yeah. Whoa, what did I do? List of depths. Okay, I don't know what I changed on there. I hope I didn't change anything there. Yes. Forgot. Why does he keep doing stuff like this? Okay. Okay, this. Oh, did I not? I don't know what you did here. It's pulling history. Okay, stop. Okay, alright, so, oops, CK, alright, Alt W, commit, boom. So this is validate BST. It's problem 4 or 5. Correcting the coding interview.